We're going to wrap up this chapter by looking at how scientists have kind of standardized how we handle these very small subatomic particles that we've discussed. And then we're going to look at the symbols that we use to represent these atoms, as well as convey information about the number of these subatomic particles. So the first thing I want to emphasize, again, I've said this in lectures past, but these atoms are already very small, and these subatomic particles are even smaller. In fact, if you were to envision an atom like the size of a football stadium, putting a blueberry right in the middle of that football field would be about the relative size of the nucleus compared to the whole atom. So because of this, these particles are very, very small, as well as the charges associated with them. So for example, a carbon atom has a mass of 2 times 10 to the negative 23rd grams. And charges, the protons and electrons, will have a very, very small charge as well. I've highlighted this number before. The charge of an electron is negative 1.602 times 10 to the 19th coulombs. And so rather than deal with these numbers constantly, these really small numbers, scientists just made it very standardized and made this convention known as the unified atomic mass unit and the fundamental unit of charge. So here's what those numbers come out to. So an electron, we basically say has a charge of -1, and a proton would have a charge of +1. Even though their actual charges, if we base them on the unit of coulombs, would be much, much, much smaller. It's a lot easier just to deal with a value of 1. And then rather than deal with the actual masses of a proton or an electron or a neutron, we just kind of use these atomic mass units as a simpler way to deal with very small particles. And notice you can see here that protons and neutrons are almost equal in mass. And even an electron, as I highlighted before, an electron is a lot smaller than a proton or a neutron, over 1,000 times smaller. The other thing I want to highlight that you should also know is where all of these things are. Protons and neutrons are found in the nucleus of an atom. Electrons are found outside of the nucleus. Now, there's some important numbers that you need to be able to identify for pretty much any atom that you find on the periodic table. First of all, the atomic number. This is always the number of protons. And this is important because this identifies the element. Now, in fact, what I'd like you to do is if you have a periodic table handy or just kind of Google one real quick, when you look at a periodic table, you see all of these elements. Normally, and I'll just kind of put, X as a generic element, you will find that atomic number either in the upper left-hand corner. So that atomic number, I'll just put AN right here, will be in the upper left-hand corner, or sometimes you might find it like upper center. But that's where you can always find the atomic number, is by looking at the periodic table. And you'll notice that every atom or every element has a different atomic number, because that's what's defined, that defines the element is the number of protons. Now, the other important number that you should be able to determine is the mass number, which is the number of protons plus the number of neutrons. Now, this number here can be different for atoms of the same element. And this term's been brought up a few different times, but now we can kind of like formally define it. This is what we call an isotope or isotopes. These are atoms that have the same number of protons. So they're identical in that manner. A carbon atom will have 6 protons in it, but different number of neutrons. Now we've talked about protons and neutrons. What happens with the electrons? Well, in a neutral atom, the number of electrons and protons are always equal. So that'd be a great thing to write down. In a neutral atom, the number of protons equals the number of electrons. Now, when that number is not equal, then the result is something we call an ion. An ion results when the number of protons does not equal the number of electrons. And I want to highlight something very important here. The way an ion is formed is it either gains or it loses electrons. You cannot gain or lose protons, otherwise you fundamentally change the element. So an ion, like for example, like magnesium. If magnesium loses 2 electrons, it's still magnesium. It just has a charge. It has become positively charged. Magnesium cannot lose 2 protons, otherwise it becomes a different atom, a different element, I should say. So how do we find the atomic charge? It's just simply the number of protons minus the number of electrons. And that value comes out to 0, then that compound, or that, I'm sorry, that element, that atom is neutral. If it's not 0, then we call that an ion. So these are the 2 types of ions we're going to look at. An anion is a negatively charged atom. And the way an atom becomes an anion is it gains 1 or more electrons. And a cation is a positively charged atom. And the way that it becomes positively charged is it loses 1 or more electrons. Again, I want to emphasize this is about losing or gaining electrons. So let's do a little bit of practice here. So table salt, if you look at a container of table salt next time you go in the store, you'll see that sometimes it's labeled as iodized. Um, and what they do is they add a little bit of iodine in the form of like usually potassium iodide, or they add iodide ions in there. And that's to kind of help with thyroid health. So the iodide is an anion of iodine with a -1 charge. So if iodine has a mass number of 127, we're going to figure out all this information about the iodide anion. So let's write down what we are given. We know it's the mass number is 127. Now, how do we find the number of protons? Or another way to say that, how do we find its atomic number? Well, that's simple. We look at a periodic table. Go to a periodic table, maybe pause the video, take a look at your periodic table, find iodine. Okay, iodine has the chemical symbol I. And you'll see that its atomic number is 53. That's the number of protons. Now, how do I find the number of neutrons? Well, that's just the mass number minus the atomic number. Because remember, mass number is protons plus neutrons, and atomic number is just protons. So if you subtract those two, you get the number of neutrons. So we have number of protons, number of neutrons. Now, how many electrons are there? So let's take this from the foundation and say, if iodine is neutral, it has no charge, then the number of protons should equal the number of electrons. But iodide has a -1 charge. So how does an atom get a minus charge? It has to gain a number of electrons. So since it has a -1, that means, so it gained 1 electron. It will have one more electron than protons. So the number of electrons is 54. If normal neutral iodine has 53 protons, but when it has a -1 charge, it's got an extra electron, it should have 54 electrons. Now let's look at another practice here. So an ion of platinum, so here we're saying an ion, has a mass number of 195 and contains 74 electrons. So how many protons and neutrons does it contain, and what is its charge? So let's kind of figure out, or let's write down what we're given. The mass number is 195, and it says the number of electrons is 74. Now, in order to know how many protons it has, all we have to do is look at the periodic table. That is the same as the atomic number. So look up platinum. Its symbol is PT, and you'll see that the atomic number is 78, which is the number of protons. So that's one of our answers there. Now, how would I find the number of neutrons? Well, I'm going to take the mass number, because again, that's protons plus neutrons, and subtract the atomic number, which is the number of protons. And that gives 117 neutrons. So now we have to figure out its charge, because the problem does say it's an ion. So it's got to be either positively or negatively charged. So this is where I'm going to compare the number of protons and electrons. So if platinum were neutral, I would have an equal number of protons and electrons. So number of protons should equal the number of electrons. But the problem says I have 74, and its atomic number or number of protons is 78. I have fewer electrons than protons. That means I've lost electrons. If an atom loses electrons, it becomes a cation. It becomes positively charged. So the charge then is 78 protons minus 74 electrons. That's a value of +4. And you want to, when you're dealing with charge, put the plus sign because that indicates it's positive. So we specifically show the sign regardless of positive or negative. So explicitly show that if it's a positive number. Now, I've kind of alluded to chemical symbols a little bit. We've looked up some symbols on the periodic table, but let's kind of dive deep to, especially to, excuse me, some of the information that we can get from just looking at the periodic table. So, oh boy, what happened here? Sorry about that. Um, so what are these chemical symbols? They're abbreviations used to indicate an element or an atom of an element. You say, well, aren't those the same things? We can use these chemical symbols to look at isotopes, to define isotopes. So, we're going to say both of those things in that definition. Now, when it comes to convention of elements, you'll notice that some of them are single letters, some of them have two letters in them. You always capitalize the first letter and lowercase the second letter. And there's a very important reason for that. Let's take, for example, um, or let's look at cobalt. Cobalt, its symbol is CO. It's got a capital C and lowercase o. If you were to capitalize both of them, so capital C, capital O, a chemist looks at that and says, that's not cobalt. That means carbon monoxide. So it's kind of it's easy or it's easy to make those mistakes if you don't realize that there's a method to the madness here that you have to make the second letter a lowercase letter. Now, as far as how the elements are named, generally it's kind of accepted in the scientific field. If you discover an element, you get to name it. Um, and some of the names kind of don't, like some of them kind of match up, like aluminum, that makes sense. Al, the symbol for aluminum, it's the first two letters, or bromine, first two letters of bromine or Br. Some of them kind of don't make any sense if you just look at it face value. Like the symbol for iron is Fe. Well, the reason for that is it comes from the Latin ferrum. So it still kind of takes it from the name, just not from the English way that it's spelled. Or same thing with mercury. Why is mercury not start with an M? Why is the symbol for mercury Hg? Because it comes from this Latin word. So you don't have to know like those specifically, but if you're just kind of wondering like how are these elements named? If you discover an element, you get to name it. Now let's talk about how we can further use these chemical symbols to give us information. So here's the generic template for a chemical symbol. So I'm using the letter X here for as an element. And we put in the upper left corner here the mass number. And we put in the lower left-hand corner here, that's the letter Z, the atomic number. And if the atom has a charge to it, we'll put it in the upper right corner. If it's not zero. So if it's greater than or less than zero, we will put it in that upper right-hand corner. Otherwise, we just assume it's zero if there's no number there. And this also helps us define isotopes. Remember, isotopes are those atoms, same element, but they have a different number of neutrons. So for example, magnesium can exist with 12, 13, or 14 neutrons in its nucleus. So if I was going to write the chemical symbol for those three isotopes of magnesium, I have my symbol here. I look at the periodic table to find the atomic number. So magnesium has an atomic number of 12. That doesn't change. And the mass number, if magnesium were to have 12 neutrons is 24. 12 plus 12. 12 neutrons, 12 protons. But the next isotope of magnesium has 13 neutrons. So I don't change the atomic number, but the mass number is going to go up. 12 plus 13. And then the last isotope of magnesium, same atomic number, but since it has 14 neutrons, it will have 26, or a mass number of 26. Now, if we're going to write out the name of these isotopes, we would just write the name of the atom, put a dash, and then write the mass number. Because it's assumed that if you're talking about, if you're comparing, say, magnesium 24 to magnesium 25, since you're talking about magnesium in both cases, they're going to have the same atomic number. So I don't have to indicate the atomic number when I name it. But what's different between magnesium 24 and magnesium 25 is the number of neutrons. And that's how I kind of indicate that by writing the name. Now, writing these chemical symbols is a little different than looking at a periodic table. So I'm going to scroll down to this next page here. When you look at a periodic table, for example, look at your periodic table and find the element lithium. So you'll find it kind of like in a box. And kind of your basic periodic table will put the atomic number somewhere at the top, usually upper left-hand corner, or sometimes maybe in the middle, upper middle. But that's the atomic number. And then if you look below the symbol, there's usually a number that's got some decimal values in it as well. So if you look up lithium, you might see something like this. Now, I'll go a little bit more in depth in this in a little bit, in just a bit. But that number there, that's down there, is known as the average atomic mass. And here's why that kind of number exists. I want you to look at this table. Now, I want you to know that you do not need to memorize this table. Okay, what I'm doing here is kind of highlighting the differences between isotopes for some atoms. So the goal is not for you to memorize this table, but I want you to focus here on lithium. Lithium can exist as two isotopes. Either it has 3 neutrons or 4 neutrons. Now, the atomic mass, if it were to have 3 neutrons, is this value here. And if it were to have 4 neutrons, its value is a little bit higher. If you look at those two numbers, neither one of those two numbers matches up exactly with that. So this is where what we call the abundance or relative abundance comes into play. 92% of all lithium atoms is lithium-7. And only about 7.5% is lithium-6. So when we're going to get into the math of this in a little bit, but just look at this, the kind of basic numbers. If a majority, a large majority of all lithium atoms that exist in the world has an atomic mass of 7, notice how close that is to the actual value. Now, why is it a little less than 7? Because about 7.5% has a lower mass. We calculate all of that together to get this average atomic mass. We're going to get to that calculation in just a little bit. I want to take a few moments and do some more practice problems. Okay, so if I give you a chemical symbol, you should be able to predict all of these things. So we're going to find the protons, electrons, and neutrons, and these are for neutral atoms. Now, when you see that term neutral, what does that mean? Number of protons should equal the number of electrons. All right, so let's start with boron. Okay, well, how do I find the number of protons? I'm going to look at the periodic table. I'm going to find the atomic number. Okay, so I find the symbol B, and the atomic number for boron is 5. Now, how do I get the number of neutrons? Well, if I look at the chemical symbol, remember in the upper left-hand corner, that's the mass number. That's protons plus neutrons. So if I take that mass number and then I subtract the number of protons, I get the number of neutrons. And then how do I find the number of electrons? Well, that's pretty easy because if it's neutral, number of protons equals number of electrons. So that's a value of 5. All right, let's look at B. So B, here we have mercury, or the symbol Hg. So how do I find the number of protons? Well, I can look at the periodic table, or notice it gives it to me here. Remember, that's the atomic number right there in the the lower left-hand corner. That's a number, a value of 80. Now I can find the number of neutrons by taking the mass number, that's the one in the upper left corner, subtracting the number of protons, and that gives me neutrons. And then the number of electrons, I'm assuming it's a neutral atom, that's what the problem tells me. So the number of electrons is equal to the number of protons. Okay, so looking at letter C, here we have copper. Number of protons, again, I find that by looking at the atomic number right here. Just as a side note, sometimes some problems don't give you the atomic number. They just give you the mass number, like that. So how do you find the atomic number? That's where you go look at your periodic table. So just as a heads up, sometimes you might see some problems like that. Now the number of neutrons, I'm going to take the mass number, subtract it from the atomic number, and it comes out to 34. And again, I'm assuming, because the problem tells me that these are neutral atoms, that means the number of electrons is equal to the number of protons. Now for D, how do we find number of protons? That's the atomic number. And the number of neutrons is going to be the mass number minus the atomic number. And since this is a neutral atom, the number of electrons equals the number of protons. And then finally, for selenium, letter E, the number of protons is going to be the atomic number. The number of neutrons is going to be the mass number minus the atomic number. And then for neutral atoms, the number of electrons should equal the number of protons. Now let's go the other way. Given this information, let's be able to write the chemical symbol. So let's look at A. All right, so the first thing we're going to look at is the atomic number because that tells us what the atom is. So I'm going to go find number 9 on the periodic table, and that's fluorine, represented by the letter F. Now that atomic number goes in the lower left-hand corner. The mass number goes in the upper left-hand corner, and it does say there's a charge of -1. So that's what I'm going to put up here. If you draw the minus before or after, I'm not going to be picky about it. As long as you just show that there's some sort of sign with that charge. Now with B, again, we'll start with the atomic number. Go look up that atom. So 43 is the element Tc or technetium. So that atomic number goes lower left, mass number goes upper left, and then the charge goes in the upper right. So for C, the atomic number is 53. So I'm going to go look that up on the periodic table. What element is that? That is iodine. And that atomic number goes lower left. Mass number is 131. As a side note here, atomic mass number and mass number, same term. So don't worry about the fact that there's that extra atomic mass number. It just means the same thing. And then there's a charge of -1. And then letter D, the atomic number is 81. That corresponds to the element thallium, Tl. And so the atomic number goes lower left, mass number goes upper left, and then the charge goes upper right. Now, let's kind of get to that weird decimal number that you find under each element of the periodic table that I refer to as average atomic mass. And I kind of highlighted why those number or where those numbers are coming from. Because the atomic mass of a single atom is approximately equal to its mass number. But here's the kind of problem. Most elements exist as a mixture of isotopes. And that mixture can have various percentage compositions. For example, chlorine can exist as chlorine 35, and it can exist as chlorine 37. Now, if you were to take the mass or if you were to count, if you were able to do that, all of the atoms of chlorine, you would see that 75.77% of all chlorine atoms is chlorine 35, and the rest is chlorine 37. Now, I know you're going to be, putting these numbers down in your notes. I do not expect you to memorize that relationship between chlorine 35 and chlorine 37. The reason I'm bringing this up is that in order to get kind of an average mass of all chlorine atoms that exist, we have to take what's called a weighted average of all of those isotopes. So how do we calculate this? Now, this is kind of like our first big math work that are going to be doing in general chemistry. So break out your calculators. Okay, pause the video, go get a calculator so you can kind of follow along with me. You will need a calculator whenever we do our assessments because these kinds of problems are going to be on your assessment. So how do we find average mass? Well, it's the sum. That's what that sigma symbol represents, of all of the isotopes in terms of their fractional abundance, that we kind of refer to as also percent abundance, times its isotopic mass. Let me kind of simplify this a little bit or maybe expand on it. Um, the average atomic mass is going to be a fractional abundance of your first isotope times isotopic mass of that first isotope. And we add that to the same calculation for the second isotope. So we do the same thing again, but we use the data for the second isotope. And then so on and so forth until we don't have any more isotopes. Now, here's the important thing. This is one of the most common mistakes students make when handling this equation. It's a fairly simple equation. The math, is easy to put into a calculator. But what most students forget is they forget to change the percentage to a decimal. So like, for example, if I tell you the abundance, the percent abundance of a isotope is 51.20%, don't put that number exactly into the calculation. You need to convert that to a decimal. Just move the decimal point over two places. And that's the number you put into the calculation. Most students, or I won't say most, uh, whenever there's a mistake made with this calculation, that's usually where the mistake is made. Students forget to do that. So, for example, the element boron is composed of two isotopes. So 19.9% of all boron atoms is boron 10. There's the atomic mass. And the remaining percent is boron 11. And there's the mass. And what we're going to do is calculate the average atomic mass. So let's set this up. So the average mass we're going to take the relative abundance of the first isotope. So that's 19.9%. I'm going to convert that, move the decimal point over two places. There's the fractional abundance, and I'm going to multiply it by the mass. Okay, so let me use a highlighter to show you where I'm getting those numbers from. This is this. This pertains to this. Now I'm going to add that to all of the data of the second isotope. So I'll convert that percent to a decimal and then multiply by the atomic mass. So that 80.1% is this value converted. And then I'm just taking that 11.0093 and putting it right there in the formula. Now, just to show the work, I plug in that first term into my calculator. I got a value of 1.99. And then I plug the second term in. I got a value of 8.82. Notice I'm keeping my units along the way. And so I add those together, and that comes out to a value of 10.1 atomic mass units. And if I know what the element is, so here this tells me the element is boron, I can kind of look at the periodic table. So take a look at boron, number 5, and your number should be very, very close. Maybe there's a couple rounding differences, but it should be very close to what's listed on the periodic table. That's a good way to check your answer. Now, on an assessment, I'm going to ask you to show the work in order for you to get full credit. because you can look at a problem like this and just say, oh, I'm just going to copy from the periodic table, call it a day. You have to show the work to demonstrate that you know how to calculate the average atomic mass. Now let's take a look at this next problem. So here this says a random element has the following natural abundances and isotopic masses. So there's three isotopes here. So I'm going to kind of label these with a different color. So here's one isotope. Here's a second isotope. And here's a third isotope. So this isn't any different than the last problem we did. We're just going to have three terms instead of two. So the average atomic mass, and it does not matter what order you put these in. So I'm just going to kind of go from top to bottom. So we'll do the green one here. So 0.9092. Again, I just did that quickly in my head, move that decimal point over two places to get to that decimal value, times its atomic mass. So that's the green data. I'm going to add that to the next term. 0.0026 times the atomic mass of that isotope. That's the blue data. And then finally do that for the third isotope. 0.0882 times its atomic mass. That's the orange data. So I'm going to do each of those terms individually. So plug those into your calculator. The first term, 18.17 atomic mass units. The second term, 0.055 atomic mass units. And then the third term, 1.94 atomic mass units. Add all those up. And it comes out to a value of about 20.17 AMU. Now you could probably look that up on a periodic table and see, well, the only one that has like a atomic mass even, like super close to that is the element neon. Now the other type of problem that you should be able to do is find the percent abundance of a number of isotopes. If I give you the atomic weight, average atomic mass, and then the atomic mass of each individual isotope, you should be able to figure out what percent each of those isotopes exists. So here's the key concept behind this. The percent abundance for all isotopes of an element always equals 100%. Now, if you look at this, you're thinking, well, I'm going to have two unknowns because I have two isotopes. Like, that's going to be two unknowns. We're going to make this really simple on ourselves and keep it to one unknown. Because if there's two isotopes, so if there are two isotopes, then make one of them X and the other 1 minus X. I know it's kind of confusing. It'll probably become clear once we start putting this into the equation. So I have the atomic weight here. So I don't have to solve for that. That's given. and I'm going to make one of the isotopes X. So, um, maybe I'll make nitrogen 14X. So what would its term look like in the calculation? Well, I would say X times its atomic mass. Now, how do I handle nitrogen 15? Well, I'm going to make it 1 minus X. That's its abundance. And then I multiply that by its atomic mass. So there's a little bit more math, a little bit more algebra involved when you're trying to find the percent abundance. So now I'm not going to skip any mathematical steps. I'm just going to go, straight through how we would do this algebraically. So this first term, I'm going to make that 14.003074x. And then this second term, remember your algebra, you're going to distribute this 15 into the 1, distribute it into the x. So you have plus 15.000108 minus 15.000108x. And now in terms of algebra, I'm going to put all the numbers on one side, and I'm going to put all the x's on the other side. Doesn't matter which side is which, you're going to come out to the same answer. So I'm going to put all the numbers over here. 0.993108. I'm going to put the x's over here. And now I just solve for x. Divide both sides by this term here. And I get that value of x. Now remember, that's a decimal. Percent abundance needs to be expressed in percentages. So how do I do that? To go to a percent, I'm just going to take this decimal point, move it over 2 places. So that becomes 99.606%. And that's how much nitrogen 14 we have. Actually, I'll use this symbol here. N14. Now, all I have to do, if that's nitrogen 14, remember we said nitrogen 15 was 1 minus X. And so the fractional abundance, the decimal value is 0.00394. I'm going to move that decimal point over 2 places to get to a percent, 0.394%. And that's how much nitrogen 15 exists. So you should be able to do both types of calculations that we've done here. Either calculate the average atomic mass, or if I give you the average atomic mass, you should be able to find either the atomic mass of an individual isotope or determine the relative abundance of each isotope. So if the math is confusing in any of these problems, please come talk to me, because most of the time when students are having problems with this, it's not a knowledge problem. They know what has to happen. It's more of a math problem and not being able to manipulate these equations properly. So please let me know. We can sit down and figure out, what's going on with these problems if you're not coming out to the right answer. Now, there are some practice problems that I have posted. um, for both Unit 1 and Unit 2. I posted those up on Canvas, and there are some of these types of problems on there. So try to go through them. There's a key there, and if you're not coming out to the answer on the key, then please come talk to me. So that will wrap up this chapter.